Hope everyone's having a lovely Thursday and is ready for this very last day in March. So everyone's ready for April next. Hope everyone is doing great. So just to get going, as we always do, very first thing, who's hiring? Now, I know that not everyone can jump in and say, because in fact, no one can say anything on screen. What I'd like everyone to do, if you are hiring, go to our Slack, the NYHackR Slack, and go to the job postings channel and put your job up there. Let us know who's hiring, and anyone who wants a job, go to job postings and get hired. It's a great symbiosis for people who want to hire, people who want to get hired, go and meet. Since I am on camera, I will take the opportunity to say that my company, Lander Analytics, is hiring for a few positions, both part-time and full-time. We're very flexible. We're looking for someone doing technical sales. That's someone who actually understands the technology and can do a little bit of selling. And a data science engineer, someone really good with Linux, but also good with the ideas behind R and Python, but mainly someone really great with Linux and databases. If you want to learn more about either of those, go to landeranalytics.com/careers. We'll post that also in the job postings channel, so it's up there. As always, the second thing we always do is pizza. So today I actually got a vodka slice with mushrooms on it. And you look at the back, has some good charring, and the front has good cheese lock, but it has been sitting on my desk for about 5 minutes now. So I'm very proud of this slice. The vodka slice is really good. I'm a big fan of vodka slices. So anyone else who is having food with us or beverages or whatever, please let us know in the chat. Let us know where you're eating from. If you're eating pizza, if you're eating some other food, if you have a beer, if you have soda, if you have ice cream, if you have tea or water, let us know what you're eating and drinking. Always fun just to have some people not knowing where to eat. It's always a good time. Next up, actually, I'm going to take a moment to share a screen very momentarily. I rarely share my screen during these things, but it's something I'm very, very proud of, and I want to show everybody. So everyone just gives me 1 second. I will figure out how I'm supposed to share just one screen. Of course, I didn't test this out. I just came up with this idea right now. And how do you share just an application? See, you would think I've never done this before. Okay, well, I'm going to share one screen then. All right. And we have, the reason I want to share this screen with you is because we have a new website. And I am very proud of all the work that went into this website. So I wanted to make sure everyone had a chance to see it. I can't tell if my screen is sharing. So Bill, can you tell me, is my screen sharing? All right, great, thank you. This is our brand new website. If you go to nyhackr.org, you can see this. You see, it's been massively redone. Anyone who saw the old website knew it was not attractive and knew that it was not very user-friendly. We have fixed all of that. Here on the homepage, it lists the most recent upcoming meetup, which is happening right now. You're at it. And it shows, hey, look, there's Bill talking about the meetup. See, we have it right here. So the homepage has that. And if there's no upcoming meetup, it has some generic information. There's an about page where you can learn a little bit about the meetup and its history and see some of its sponsors. Now, the big improvement here is past talks. This actually is so much more useful now. It highlights the 4 most recent talks to show you, hey, who spoke most recently. And then the search capability is so much better. Let's say you just want to search generically for ggplot. You search up here and it filters it down to all the talks over the years that have ggplot. If there's a video, there is a little play button right here where you can see the video. If you want more details, you can come here and click the plus button and it gives you all the details about the meetup, including where to find the links. Let me see if I open that. That should take us right to the slides too. So you have both the video under the more details and the video, if available, right here in the table. You can also search for individual speakers. Let's say we want to search for Hadley Wickham. You come here and you can see all the times he spoke at the meetup. And if there's a video available, the video is here. And you could also click the plus sign to get to the slides and get more information. So we're really excited about this. The events tab will show you upcoming events in the community. Right now we have the New York R Conference, which I'll talk about in a little bit, and the government conference coming up in December, and we'll post other events as they occur. Then under the More tab, we have our pizza poll, which we haven't been able to collect data for 2 years, but the chart actually works now. It actually looks right and is usable, and you can actually zoom in and scroll across it. It's a big, big improvement. Also under more are books. We have a very large community, and a lot of members of our community have written books. This is a place to come check out books written by the community. And if you notice, every time it loads in a random order. This way you can always see what comes up at top. If you've written a book and I have not included you up here, let me know and we'll get your book added up here. We like to share how all this cool stuff everyone's doing. And there is a contact page if you want to get in touch. Here's a great way to contact us and learn more about the meetup. Let us know what's going on. There is a button here for Slack, so you can get to it more easily. If you don't remember the long URL, just come to nyhackr.org and find the Slack button. And these are links to our Twitter and our GitHub for the meetup. So I'm very proud of this. And I want to give a big thank you to Joe Marlowe and Nicole Del Judas for building this. They put a lot of effort into this. They made it really, really beautiful. Those of you who saw the old one, you know this is 3 generations forward for how amazing it is. And by the way, it is written in R, because of course that's how we do things here. So if I can just get a big virtual applause for Joe and Nicole for all their effort they put into doing this, it was really amazing. I am really, really excited by everything they did. So thank you everyone for making this for making it so amazing. Again, nyhackr.org to check it out. A few more announcements, then we'll get going. We are hoping to return to in-person. And don't worry, there will be in-person and virtual. We will do both. But we need space. Getting space in New York City was hard before the pandemic. It's harder now. So if anyone wants to host us for the meetup, to have 100 data scientists come into your office, hopefully in a COVID-safe environment, let us know. We are looking for April, hopefully if there's another surge and beyond that. So be in touch with me, go to that contact page on the newly redesigned website, tweet me, email me, comment on my GitHub, whatever you want to do. Let me know if you have space. We would love to have you hosting us. It's a great group of people. Let us know. We would really, really love to have someone host us. So please message me. Our normal hosts aren't open yet, and we want to have a big repertoire of hosts. We want to share the love and be around as many people as possible. So let me know. One thing I forgot to mention about the website, if you do want to make a contribution to this newly beautiful website, github.com/nyhackr/nyhackr. It's public, all the code is publicly available. Head up there and we'd be happy to have you contribute. Coming up in June, in person and virtual, the New York R meetup. We are very, very excited for this, June 8th through 10th. It'll be both in person, hopefully, as long as nothing goes wrong in the world, and virtual as well. We have workshops on June 8th. The workshops are being led by Max Kuhn, Yaron Janssens, Dean Natali, Malcolm Barrett, and Lucy D'Agostino McGowan. And we have a whole lineup of speakers. It's really great. We have Asma Toomey, Jennifer Hill, Andrew Gelman, Sarah Catanzaro, and Wes McKinney, and amongst many other speakers. I didn't want to highlight everybody, I just need to highlight a few. So it's really going to be awesome. Use discount code NYHackR for a 20% discount. We'd love to have you there. We're also looking for anyone who wants to sponsor, wants to have a booth. Let us know. Contact us if you want to be a sponsor. Also, we're looking for artists. A few years ago, we started having an art auction where people would make art either by hand or generative. We would auction it off and all the money would get donated to the R Foundation. The money goes to good cause and it's a lot of fun and someone gets your artwork. So if you want to donate art and have the proceeds go to the R Foundation, be in touch and we'll happily auction off all of your art. Then lastly, today, Manning Publications has given us a discount code to share with the group. So if you would like a 35% discount on any of their products, you can go to Manning's website and use code, and this is a lot, this code, and we'll put it in the chat, MTPNYSTAT22. I'm not sure where that chat code came from, but that's what they have, and we'll put a link, MTPNYSTAT22 for 35% off. And for all of you here today, we are going to choose three random winners. And we're going to be giving away these following books: Good Code, Bad Code by Tom Long, 5 Lines of Code by Christian Clausen, and Street Coder by Sadat Kampanoglu. So at the end, after Bill's talk, before questions, Yeah, before the questions, we're going to give away these 3 books to people who are present here right now. So we're looking forward to giving those books away. Looking forward to this great talk. Bill is he's now a 3P. He's a member of the 3 Timers Club. He's given a few excellent talks before, and we are really excited for this. So everyone, please welcome with a virtual applause Bill to the stage. Thank you. Thank you.
Thank you. Can you hear me, Jared?
I can hear you.
I can hear you. Perfect. Share my screen. And go full screen. Oops. There we go. Perfect. Okay. So I'm super psyched to be here. This is a very cool topic, in my opinion. We will be today unpacking Tesla's autonomous driving models, an outside-in view. Before we start, big thank you to these people. They helped me learn to present better, revise the content. It's a much better presentation because of these people. So for that, thank you. And this was pretty cool in the headlines. Some of you may or may not have seen this, but as of yesterday, Waymo began full driverless taxi. Very timely, very relevant for this topic. Just to kind of set the top context a little bit before getting into the actual agenda. Tesla does this really cool thing every 18 months or so. They present 3-4 hours on their thinking, their methods, their approach to autonomous driving. The most recent one was in August of 2021. Prior to that was 2019. They open source their methodologies to a certain degree, and that's really cool, I think. But if you look at the headlines, they were almost across the board captured by their announcement of building a robot. And to me, that's the wrong emphasis, because they're at the frontier of a lot of cool methodologies, and that's what we're going to talk about today. So there's really 3 things would like you to take away from today's discussion. First is their approach to vision. And the big thing there is vector space. Image, single image, one label, vector, composite image, composite labels. Really cool. We're going to go through the intuition of that. We're going to go through what it looks like from a data perspective and what it looks like from the network. And the implications are pretty profound. 2, we'll go through the planning module and the network architecture. And lastly, we'll talk about the so what of it. So how is this meaningful or relevant to me in different industries? And we'll just dabble on a tiny code segment that captures an important part of the method. There's lots of good resources on the web for the deep learning methods. There's one in particular I'd like to highlight. Myself, I work at Bank of Montreal. I guest lecture at Columbia. I'm a student at Georgia Tech. Here's how you can reach me. And we're hiring too. Personally on my team, data scientists, senior data engineers. Many of my colleagues in the anti-money laundering group, cybercrime, AI. It's a cool bank. I've been there for 2.5 years now. It is by and large filled with smart, ambitious, and kind people. So to me, that's a very cool combination. It has a very distinctly, for a good reason, Canadian feel to it. And in a twist of irony, the Bank of Montreal is headquartered in Toronto. Okay. Disclaimer, I'm in no way, shape, or form associated with Tesla. I'm more of a groupie. I try to absorb as much information as they put out, and they do put out a lot. It's just kind of cool. It's They do a lot of cool stuff. I try to internalize it as much as I can. The two folks here on the screen are rock stars, in my humble opinion. So I try to learn from them, and I try to think through what they're doing, how I can apply that in my role. So being an unsocialized teenager, taking lots of things apart, putting them back together again, reading lots of science fiction, I began to expect that we were going to have flying cars and jetpacks. This autonomous driving, to me, is in a similar ballpark. And that's part of what motivates me. Okay. The big transition you're going to see here is from image space to vector space and multi-headed deep learning models. We'll go into the network there. And what you see here on the lower right, this is the network architecture for the vision components of Tesla's autonomous driving. And one of the goals for today is to provide an intuition of what this is and to provide a view of the architecture that put this together. With the deep learning, it's much less about the features. The network figures that out for you. And the thinking goes into presenting the data and the architecture. So for that reason, that'll be the focus of today's discussion. So hopefully at the end of this, you'll have a good intuition of what all this is. And to put this in context, in the broader architecture picture, there's the vision component. So what comes in are pictures, what goes out are objects that are recognized in time and space, the vectors. Those feed into a planner, which has a lot to do with optimization. We'll touch on that. So those are the two big parts we're going to touch on today. Okay, let's get that. Okay, what is the intuition of vector space? For me, as I was unpacking this, getting a mental map of what this is, and shout out to JD, that was a solid tweet. I need that mental map to put things together. So that's the journey we'll go on together today. That mental map should drive us to an intuition. A Tesla has in it 8 cameras, 1 rear facing, 2 here by the doors, 2 here by the fenders, and 3 forward facing cameras this way. 8. 8 images, and that's going to be the entry point to our network. So here's a visual of what those 8 cameras see. They come into a neural network, and the vector space is visualized here on the console. So here, the red lines are the curves, the white lines are the lines on the road, and it's the network that's painting those vectors. So images in, vectors out. So let's get a little deeper into the network. So a few years back, Tesla was operating in the image space. Well, what does that really mean practically? So each camera feeds its own segment, its own backbone of an object detection network. Each one of those detections, the predictions of what those objects are individually, come out and are fused together, come into the planning model, and the planning model is going to output, stay in your lane, keep your distance from the car in front of you. It's kind of the scope was highway only, forward only. But the key here is scalar images in, scalar detections, 8 cameras, 8 detections, fuse, and act in vector space. So what changes with vector space? Here we go. So in vector space, and we're going to talk a lot about this, but the essence of it is take your 8 images and land them in one raster. So 8 cameras, one composite raster, one vector of labels, and that's what we're going to feed into the object detection. Then we model, and in the years since the previous version, as they aspire towards the full self-driving, the sophistication of the model is much greater. So now what outputs is a plan, a driving plan for the next 10 to 15 seconds or so that estimates position, velocity, acceleration. Pretty cool. So here's a visual of what predictions look like in image space. And everything we see here on this, every prediction we see here is based on a prediction from a single image. And there's a lot of predictions going on here. We could see the lines in the road, the curbs, the stop signs, the cars in front. Pretty cool stuff. But there's 2 big challenges here. Okay, so what we're seeing here is each individual image predicting the curbs as the car is getting summoned. And image by image, the predictions are pretty good. These curbs, those are pretty good estimates. But where it starts to fall apart is in the fusion of those predictions into vector space. So this on the bottom is a visual of what that fusion is doing. And you can see it has a jagged quality. It's very discontinuous at places. And it's a very, very challenging vector space to drive in. Challenge number 2, object detections where the object spans cameras. So here we have one truck visible in 5 of the 8 cameras, and each image has a very different perspective on the truck. So to weave these together, to fuse it together, to say that this is really one truck is a really challenging thing to accomplish. Okay, so first, what I'm going to do is show the benefit of operating in the vector space, and then we'll start to unpack it. Same visual, curves and lines. On the bottom left is the fusion of these estimates in the image space. On the bottom right is the fusion of these estimates in the vector space. And this is clean. This is something that you can drive to. All right, so the transition to vector space has very profound implications for how we think about labels, data, and the network architecture. I tend to think of data-centric, so we're going to start with the data and the labels. We'll go through that end to end, and then we'll backtrack and come through the network architecture. So labels, vector labels. Okay, airplane reference. It's kind of hard in Zoom. There's little feedback. But one of my favorite movies. All right, so this is going to be an important image that we're going to see throughout the presentation, but we're still operating in vector space. These are going to be features that drive the network. And ultimately, with this pixel here, we want to detect that it's a car. A view from image space, a view of the features. But let's rethink this in a vector space. So ultimately, these features are going to land on a pixel by pixel raster. So let's imagine in this raster, this yellow box, and we know that's the curb. How does that project out into a vector space? So what we do is we connect that same place, that same location across multiple images. It's a projection. If we could do that, it's great. It's a challenge because to do this with precision is not easy. And that's a big reason why the image space doesn't work. But staying on the thread of labels, we're going to talk about manual and auto labeling, and we'll touch on simulation at a later point. But they've really fundamentally transformed how to label. First is manual. What we're looking at here is a view of a human labeler. And this is the workstation, the tool that they're using to label. So let's unpack this a little bit. This is a small video clip that the operator can move around, the orientations, the perspectives, and these little blue lines that are changing. Those are the labels for the curbs. What makes it a vectorized? Well, what makes it vectorized is as the editing is occurring here in the video, it is simultaneously occurring in each of these images. One edit across vector space. The benefit of this is a massive increase in throughput using these tools. But this is part of the bridge from the image to the vector space. So we often hear the term big data. That doesn't exactly describe the nature of what needs to be solved here with the autonomous driving. And the reason is, to crack the code with autonomous driving, there's a massive quantity of edge cases. So it really can be thought of both the big data and a specific data problem. And here's an illustration of what that might look like. So the context here is driving in the snow. The truck passes on the left, throws up some snow, and the scene becomes obscured. Okay, that's not, and you can see as the snow comes up in the image space, the label, the detection of the objects in the image degrades dramatically. Kind of makes sense. Fun fact, there are more than 2 million Teslas on the road. And inside each Tesla, there are 2 high-speed computers for vision processing. One is driving the car. The other serves multiple purposes. It's testing the next version, but it also serves this purpose. And they can ask the fleet. So they'll take a video of a scenario, an edge case, where there's grossly insufficient quantity of labels. And they'll say to the fleet, send back clips that look similar to this. It's kind of cool. The result in this particular case are these clips. So in the span of a week, 10,000 of these clips were collected and labeled. And the impact to the estimation is here. So on the left, image space. On the right, auto labeling, vector space. And it's kind of cool. You see the snow, oh, sorry about that. You see the snow thrown up, but the prediction persists across the snow. I'm going to skip that. So these are some examples of how these clips are used. I'm going to brush over this, but it enables Tesla to massively increase the throughput of what they can label. Okay. So this is pretty cool. Here, what they've done, these lines represent curbs and lines in the road from the same location across different trips. And it's a different way of aggregating labels, but if you aggregate these over time, it produces a much crisper, much more effective labeling of the surrounding. Skip that, skip that. Okay, so vectors in this context exist both in space and time. up until this point, we've talked mostly about space. Let's take a look at how vectors play out across time. The problem presented is there are gaps in memory if we're working in an image space. So what's an example? You're stopped at a light, a car drives in front of you. As it drives in front of you, it's going to obscure what's behind it: pedestrians, signs, other cars. There's a lack of memory. So there's two things that are presented to solve that. The first one, I'll talk a little bit about a spatial RNN. The second comes in on the planning side and the vision side. We'll talk about that in a little bit. So what they use, again, this is in the intuition. We'll talk about the architecture in a bit. It is a spatial RNN. And the benefit of the spatial RNN, a recurrent neural network, is it lays out the RNN on an XY coordinate. And by doing that, you can focus the predictions on the immediate space around the car. And what that enables is a better estimation of the roads around you. The other benefit this drives is it enables predictions even when there are temporary occlusions, pardon me. So what we're seeing here through these cameras and through this visualization, the blue blocks are the estimates from the vector space or the video. The orange blocks are the estimates from the single frame. And what the blue can do that the image can't do is when the truck drives in front, we know that there are two cars behind it. Okay, so we're getting closer to unpacking the architecture. But before we get to the architecture, we're going to talk about planning. And planning, so what's going on with planning? So the place where we're at now is we have the vision networks have run. They have estimated the world around us in terms of curbs, lines, other cars, pedestrians, speed, orientation, road surface, raining, snowing. So we have all these estimates. What do we do with it? We need to plan. And planning is an optimization problem. So it's framed with getting to the goal while maximizing for safety, comfort, and efficiency. So a couple things about optimization in this particular problem. The space is non-convex. And you could easily get caught in lots of local minimums. The other side of the problem to solve for is it's a very high dimensionality problem to solve for. So the approach is to carve off subcomponents of the space that we're going to solve for to create subsets of the broader space that have convex qualities. So think of it as a hybrid. It's both core search to get some arc that we're going to anchor to. And then within that arc or convex corridor, as it's referred to, we'll do convex continuous optimization. So here's an illustration of what that looks like. Imagine we're this red car here, and our goal is at the next intersection to make a left. In between, what we'll need to do is move over 2 lanes to the left. There's a couple of options we can take given the other vehicles around us. One is we can slow down. And you can see that here. The top graph is position. The bottom graph is velocity. So this particular plan says to slow down. Not great, doesn't give a great comfort experience. Another option is we can speed up, accelerate. But the risk here is if we accelerate and don't make it around the next car in time, we'll miss the turn. Ultimately, what happens is there are thousands of potential plans out there. And that's what's represented in these graphs in terms of position, in terms of velocity. And that's where the optimization comes in play. In this particular instance, roughly 2,500 potential plans that the searching and optimization for occurs in milliseconds. And ultimately, one path is selected, and then the car, that's the white path, and the blue path here is the actual trajectory the car takes. So we're going to look at planning in a different context, and that's parking. So the goal here, the car is physically located here, and we want to park it here in green. And we're going to go through 3 different approaches that have dramatically different variants in the space that they have to search. The first option is going to use the edges of this parking lot as the bounding criteria for the search space. Ultimately, the space here, it's optimizing for Euclidean distance. And given all these local minimums the car lands in, is almost 400,000 different paths to get here. Yes, it gets there, not so efficient. The second method is, this is where the convex corridor gets introduced. There are these arcs, there's roughly 5 of them, and the paths are going to be anchored to that arc. So here, within the arc, we're looking at something that's much more convex. Still gets caught a little bit with some of the cones, but eventually it's going to get there in the neighborhood of 22,000 paths. Pretty good. Ultimately, the third method they approached is a combination of Monte Carlo, states and actions. And I don't know this explicitly, but they alluded to the fact that there's a reinforcement learning quality to this. They connected this approach to things like AlphaGo, which is a deep reinforcement learning problem. But the idea is to scan the environment, to ascribe rewards and states and actions, and come up with a heuristic that will dramatically reduce the set of plans to explore. And this is the impact of that. Ultimately, it's dramatically smaller in orders of magnitude. The quantity of plans that are the space, the search space that is explored. So we've covered the intuition of vision. We've covered the planner, both from an intuition and a methodology step. The next big thing to cover is the architecture of the network. Okay, so hopefully, when we're finished with this, we'll have a reasonable understanding of what's going inside this network architecture. Okay, so the first step is raw images are coming in. We want to introduce those into the network. They're ultimately going to become rasters. And the architecture that Tesla chose here is a recurrent neural network for this backbone. They chose RegNets. The reason for choosing RegNets is they have a very nice trade-off between accuracy and latency. And what you can see here, the interesting part, as the features progress along this backbone, they'll start with a higher resolution image with fewer channels. and they'll land the feature space in a much lower resolution with a higher channel count. Why? The view is that with the detailed pictures, you can get more effective predictions within a particular image. With the lesser resolution and the greater channel count, there's a context for the images that's very useful for the predictions. So recurrent neural networks, RegNet blocks a variance in resolution and channel count. So we'd seen this image before, and where this plays out is this pixel's a car. That's sort of the low end, the high resolution, but it's in the vanishing point of the road, which is here with the less resolution, the context, the higher channel count, and that context makes it more effective to estimate that this is in fact a car. The way to do that is with the feature pyramid networks. The reason is these bidirectional feature pyramid networks are very good at sharing information across these different streams. Up here is the context, up here, lower resolution, down here is more image focused with the higher resolution. Okay, so we have raw image, we have recurrent neural networks, RegNet blocks, and we have bidirectional feature networks, feature pyramid networks. All right, we're assembling this slowly. Next, so what that's going to give us is this raster of pixels. In deep learning, these are the features that the network is going to learn, or parameters. So what comes next are detection. We want to detect something. Is it a car? Is it a bicycle, a pedestrian, etc.? The approach they used here is YOLO. YOLO-like is what they say. And the benefit of YOLO is it can do the prediction in a single pass versus having to do multiple passes through the image. It's efficient, it's accurate. At the end of this, you're going to get a binary on these pixels, car, no car, things of that nature. All right, so now this is a cool pivot point. The reason it's a cool pivot point is we're going to get into multi-headed networks. It's a modular approach to deep learning. We don't want to just predict cars, we want to predict a lot of different things. Signs, traffic lights, curbs, pedestrians, mailboxes. Each one of those is its own prediction trunk. But you don't want to take the cost of creating these rasters and going through the RegNet and going through the feature pyramid network. You want to take that cost, do it once, and then apply it across multiple prediction heads. So you get the benefit of execute once, use many times. You can cache the features here in disk and train each and every one of these individually. You can swap these in and out. And then periodically, you can choose to backprop and retrain the entire network end to end, but you don't have to. Okay. So in short, one image, many predictions. But we're still in the image space. So we still are working off of a single label. We're still we haven't pulled together the vector space yet. So how do we get there and what does it look like? The thinking is we're going to have a backbone to create the rasters and features for each and every one of the pictures. We're going to land them here in something that will enable us to estimate in vector space. So just to refresh on this, the vector space is one pixel, one feature connected to many images. One of the big challenges in doing this well, is getting the position right across a lot of different perspectives. So granular accuracy is needed in space with positions, accurate positions. What kind of network architecture would that suggest? Transformers. So this is where things come together. This is where we start the transition into vector space. So at least from an architecture view. The really nice thing about transformers is they have an encoding specific for the position. And the network learns what the meaning and value of that positional encoding is. So if we pivot just briefly into natural language processing, where transformers are used extensively, the position of a word in a sentence or a paragraph has meaning. And that position of each and every word is a feature inside the deep learning network. And that's a big part of the value of the transformer architecture. So essentially, what's happening here is we come up through the transformer. Where's my mouse? Sorry, it's on the other screen. There we go. So all of this is the transformer. We have the positional encoding here. There's the context of what the image is. It comes through a multi-layer perceptron, and ultimately it's going to come into two places, a query and a key value pair. And it's what the query is saying is, hey, I'm a pixel, and I'm looking for stuff that's related to me. In the key value pair, it's saying, it's each image broadcasting, hey, I'm part of a curb, and I'm seeing this kind of stuff. It's raining, I'm about to turn. And these two, the key value pair and the query, they have a multiplicative effect that brings them together. And all of this gets optimized by the deep learning network. So looking back, all of that network architecture comes to play to bring all of these images together and to do the estimations in the vector space. This is a visualization of a car driving in traffic. And the thing to look here, the thing to call out is the difference between the blue vector space predictions and the orange image space predictions. And you see how the orange has this jittery quality? What's happening is as cars cross image boundaries, it's very challenging for the network to place where that car is. And whereas in the vector space, it's a far smoother estimation. So we've gone through this portion of the network. I'll touch briefly on these. So we've detected all of the objects. What's going to happen is they're going to get pushed onto a queue. They can get pushed onto the queue either through time increments, through space increments. That's what's going to feed all of the optimization. And that's what solves for the memory. So that a car has passed in front of us, that these features are on a queue, we retain it. And the network can know what's behind this car. There's a whole method in terms of when to push on queue. It's over time, it's over space. We spoke about that. I'm going to skip that, but I did want to show with the spatial RNNs, what this visualization is showing is across each channel, the channel is anchoring to a different estimation. Some are anchoring to curbs, some are anchoring to the center of the road, others are anchoring to the texture of the road. A different view of the spatial RNN. See? And that's the essence of it. That's the essence of Tesla's architecture. Okay. Much of this is coding. Pardon me, is the architecture of the network. But I did want to share this code fragment because it's I think captures part of the essence, and at least it brought it to life for me in terms of how to optimize across all these different heads on a network. And the essence of it is each head has its own loss metric. Whatever loss you want to anchor to. It could be cross entropy, mean square, doesn't matter, you choose. And you calculate each loss individually across your X's and your labels, your inputs and your labels, and then you bring it all together. You bring them all together into one total loss with weights that you can choose against each loss. So when you forward prop and back prop across the network, what the deep learning network is going to do is it's going to minimize this total loss. There's lots of great sources online if you want to see how to code these, but I wanted to highlight this particular portion of the method because it's very relevant for some of the opportunities or hypothesis would be a better way to say it, that I and my team are exploring. So what? So it's cool stuff in the driving space. How might that apply to other industries? It has, to me, the vector, the way it's presented by Tesla, the container for the vector is a raster. But what if we think of that container in different contexts? It could be a customer journey. It could be a shopping basket. It could be a functional perspective. If you're at a large corporation and you want to have a basket of cross-sell models across a variety of products, one hypothesis is to make each product a different head on the network. They can share features. You can spin off features that are specific to products. And a potential benefit is that you can take many models and combine them into one. I don't think it would work where you'd want a bespoke model, where you'd want to eke out every basis point of lift because of the economic impact. But if you have a few dozen models that are cross-sells, that are fairly generic, the hypothesis is perhaps do that as one deep learning multi-headed model. Okay, so it's kind of fun to talk about flying cars, jetpacks, self-driving cars. But let's look at this through an economic lens for a moment. According to the US Census, in 2017, there were 3.5 million truck drivers in the United States. So if we think about the potential impact of these methods to the economy, to society, it's potentially, it's this massive game changer that has massive, massive impacts potentially. You can debate, will it happen in 5 years? Will it happen in 25 years? I don't claim to have the answer, but in my simple mind, it's not a question of if, it's a question of when. All right, so I know before we talked about questions, Jared, you wanted to do some giveaways.
Before the giveaways, a round of applause.
Thanks.
That was a really great talk, a lot going on in there. It seems like it must have taken you a long time to develop this deep understanding of it. So I appreciate all the prep work you did.
It's,
Where is it?
yeah, it was fun. It was a fun exercise.
Good. I'm very glad. I'm very glad you had a good time. Good time learning. I had a good time watching you, so I'm glad you had a good time learning it. Before I do the giveaways, if anyone has questions, I forgot to announce this before the talk, post them either in the chat here in Zoom, that's the non-preferred way, or in the Meetup channel. On the NYHackR Meetup, there is a channel called Monthly Meetup Chat. Go post your questions there. It's easier for me to copy and paste to take notes with. But please, if you have questions, while I'm announcing the giveaways, now's a good time to think of those questions or go ahead and ask them. So I'll give everyone a chance to ask the questions as I do giveaways, and we'll have some, we'll grill Bill a little bit. So the first book, Good Code, Bad Code by Tom Long, is going to Thomas Cason. Thomas, congrats on getting a copy of this book. To redeem your book, message Nicole Del Judas. That's you'll see her in the Zoom chat. Either message her on Zoom before we end, please, or on Meetup. She's at the NYHackR Meetup. Her username is just Nicole Del Judas, or email her at Nicole@landanalytics.com. There's 3 ways to get in touch with her. I'm out of ways. So use one of those 3 ways to get in touch with her: the Zoom chat, her email, or NYHackR. Get your book. The next book, 5 Lines of Code by Christian Clausen. The winner for this is Connie X. Connie, same thing. Email, Slack, or Zoom Nicole. If you're going to do it Zoom, do it now before we end it, because otherwise you won't be able to do it. So, but Slack, you have more time. And then the third book, Street Coder by Sadat Kapanoglu. The winner is Dmitry Mileshko. Dmitry Mileshko, congratulations on your book. Same thing. Go ahead and message Nicole. And by the way, just so everyone knows, this was done randomly, as we always do all of our giveaways. We didn't literally pick names out of a hat, because we don't have a hat or printed names, but it's essentially the same process as that. So congratulations to our 3 winners. And remember, everyone else who didn't get a book, 35% off is a big discount. And you could do that with code MTPNYStat22. Any of Manning's products, you can go get a discount on. So with our 3 winners, congratulations. Let's get into some questions. Let me just check this off and get to what I've compiled. The tool question. I think one of your slides sort of give a hint, but what are they using for the neural networks? Is it Torch? Is it Keras? Is it something else?
They never specifically get into that. There are hints around PyTorch. The gentleman, Andre Parthe, who's the director of Vision, he created the Stanford Convolutional Neural Network class and posted that online. That's all in Torch. Mm-hmm. So I'm pretty certain it's Torch, but I cannot say that with certainty.
And you did mention YOLO. I know the YOLO v5 is Torch-based, but there's like 4 other YOLOs. But you said it is YOLO-like, so that might give a hint too, I guess, right? If that is Torch-based, maybe that works in there. That's
right. That's right. And there's a lot of other folks that I follow on Twitter that tend to gravitate towards Torch. So if I had to bet, I would say Torch, but I wouldn't pound the table here with certainty.
That's fair. And again, you might not know this question, but like any clue they've hinted at how long these models take to train, and like how many machines and GPUs they're using to train them.
There's actually a very cool story beyond that. So the whole AI day spanned 3 hours. The vision and the planning that we went through was approximately an hour and a half. Beyond that, they announced that they have a full stack development. They're a vertically integrated company. So they want to make all portions of the Tesla. They're bringing that perspective to AI. What does that mean? That means they have their own chip. They have their own version of a GPU. They have their own cluster. They're building out a massive, massive farm of hardware that is specifically designed and tuned for AI. So they have a massive amount of hardware behind this. It's actually very cool. I can throw the link on the presentation, but they're investing a ton into a fully vertically integrated AI solution. And I'm purely speculating here. It wouldn't surprise me if they brought that to market as their own product, but that's purely me guessing.
And when you say the product, you mean like the AI solution or the actual hardware itself?
The hardware.
So you did allude to that they have open source some stuff. So it'd be cool to open source some of their software. That'd be really awesome. Or even more of it, I suppose.
That'd be very cool. That would be very cool. The other cool spin on it was just before they announced that they're building, they're bringing to market a robot product. And it was just in the headlines this week because they're saying it will be on the market in 2023. They portray themselves not as an automobile manufacturer. Rather, they see these as robots with wheels, given the amount of intelligence that's baked into it. I thought that was kind of a cool way to position it.
It is cool. One logistical question, then we'll get back to content questions. There was a question, will this be recorded? Will it be shared? Yeah, the videos will go up to our YouTube channel within a day or two, along with the slideshows. And you get all that information at nyhackguard.org, our brand new website. So anyone looking for the recordings or the slides, go there. So back to content questions. In switching to vector space, how important are synthetic data sets?
That's a great question. There's a whole thread here, which wasn't touched on at all. There are three ways Tesla's approaching labels. One is the manual labeler that we saw with the video clip. The other is poll the fleet. The third is simulation. Didn't have time to get that in here, and I didn't know if it would resonate with this audience. They're doing a massive amount with simulation. Where simulation in this context, meaning we dream up an edge case, a goofy one, of people running down the highway, and they simulate it in a very realistic way with the texture, the light shading, and by simulating it, you now have new data that is fully labeled. So that's a big part of their strategy for managing the edge cases. So I'm projecting into synthetic the simulation, and I think that's on solid enough ground because those are not real labels; they're completely human computer generated, and they portray that as the interface, an interface between human and computer.
Yes, and I imagine by simulations, they also do like you showed how they play out scenarios. If you turn left, what happens? You turn left at a different angle, what happens? And I wonder if that gets fed back into the loop too somewhere.
Totally. Or if there's a new car that's going to hit the road that's not in production yet, get ahead of it. Put it into your simulation, label it, and throw it into the next training run.
And do you know if these simulations of these weird scenarios, like they occur for the lighting, like on a rainy day, a cloudy day, a sunny day, does that get into
very much? Like if you look at them, the detail in there is remarkable because usually the tell is in the perspective of the shadow, and it looks frighteningly accurate.
Now, there's another question. They probably have thousands of features collected by camera. Do you have any sense of how these inputs are selected by Tesla engineers, how they properly do feature selection and engineer the features? Did anything come across about that?
So I think the question is how to feature engineer the data that comes through cameras versus what's simulated. At least
I'm not quite sure, because I'm not sure about the context of this question. It's like, yeah, how do they, if they have thousands of features, I guess, what is a feature? I guess it's the pixels. So maybe there's not a lot of, how do they decide, like, should we look at shadows of objects or should we look at, implied heights of objects? Maybe that's the question.
So one of the cool things about the deep learning is that those rasters, that pixel that says car, not car, it has an array up against a torch array. It's like a lot like a NumPy array. And each bit has essentially a deep learning equivalent of a coefficient. And the backward propagation is saying, well, if it's this value, what is the total loss? Do some gradient descent. That gives you the direction to change it. Change that single pixel coefficient or feature. I'll use coefficient and feature interchangeably for the moment. Come up with a better coefficient, and that's the essence of the back propagation. So think of each feature as a deep learning equivalent of a coefficient.
Okay. I guess if the coefficient is close to 0, the feature doesn't matter.
That's right. Exactly. That's exactly it, Jared. Is that the deep learning is ascribing the value, and that we're not necessarily in this context. There's nothing said. We didn't talk about at all tonight any kind of feature engineering. The thinking is in how to architect the network. The thinking is how to present the data into the network.
I wonder how, I wonder if they have more insight, if they give more insight into how they do present it to the network, but there's only so much they give out. Right.
That's right. But one of the hard parts is to train these multi-headed networks. They're very, very challenging to train, but if you get it right, there's a lot of benefit.
Speaking of complications, what do they have anything, or they talked about anything about like dirty or smudged cameras?
That is a great question. So it turns out, as the Tesla fleet evolved over time, there are nuanced differences in the cameras, which becomes very important to how, I don't know, let's make up an example. Jared has a new Tesla and I have an old one, right? We might have different, what's the word I'm looking for? Distortions, slight distortions in the two cameras. And that was a big thing they spoke to, is that they had to almost bake features into the network to account for that. Because if you don't, the new Tesla that you have, the old one I have in this made up scenario, would present very different to the network. So they have to normalize that.
Or even where over time, your camera started out as a different camera, but then you've been driving it for 7 years. These cars are going 80 miles per hour, hitting bumps, things get damaged.
That's right. That's right. That's a great point.
And do they mention at all if they're using like LiDAR or radar in addition to visual wavelengths or sonar?
They made a very conscious design decision to eliminate radar. Their view is humans drive based purely on vision and sound, and that radar is an unnecessary complication. So they have very publicly and visibly pushed to eliminate radar out of their models. The cars, many of the cars have radar, but they're pushing to train only by vision. Or no, I should say they're training to use no radar, eliminate radar. I do believe they've hinted at that they might use sound too.
So, and I guess LiDAR counts as radar, so that's they're eliminating that as well. But interesting about sound. Now, when you say sound, is it like sonar? They're sending pings, or is it just they're capturing sound, like things they record?
I've only gotten hints at this. So in preparing for this, I actually went through the owner's manual. And they talk about microphones in the car. What its use is, I can conjecture, but wouldn't know.
Okay. All right. That makes sense. As humans, what they see. Now, that's actually another question. What wavelengths of light are those cameras capturing? Is it like ultraviolet to infrared, or is it just literally visual spectrum?
That's a good question. I don't have an equally good answer. I do know that they They've standardized by 1280 by, I think it's 960 frames, 35 hertz. And that some of the cameras are fisheye, so you get a broader field of view. You got me curious now. It's a good question. I haven't heard anything that talks to a visible frequency, but they could, in theory, expand beyond what we can see.
Because you think about it, like, and I know satellites use different wavelengths to get through clouds, and fog is just a cloud on the Earth, right? So maybe they need something to get through the fog.
Totally. And it wouldn't, the economics of it would be minimal.
Yeah, just another, just another channel.
Totally.
Okay, cool. And you talked about the losses being computed all together. So I guess a few parts of that. One, how do they decide the weighting for each head, right? And because you said, you have like the different types of loss, you multiply it by its weight to come up with total loss. So A, how do they come up with the weighting, how much each head is worth? Is that itself optimized, or is that humans, choosing it? Then also, why not just compute the loss for each head separately and then combine them?
So I'll speak generically because I haven't heard anything publicly said about that. But they do train each head individually. It's a great way to split work across teams, right? You're the team that's dealing with stop signs, traffic lights, pedestrians. So it compartmentalizes the problem very, very nicely. And they do cache to disk features along the way. So if you have an intense focus on a particular head of the network, you can do that. So there's lots of design sprints that are focused on particular heads, but ultimately you have to bring it all together. I haven't heard anyone publicly talk about how they weight it. What I've done in my shop is we come up with a weighting. In theory, you could bake that into the network to weight that, but there's a lot of design considerations if you have unbalanced data that might that would be a big factor in how the model might react to that.
Okay. Great. That's all the questions I had so far. If there's any last minute questions, now's the time to do it. I'll give everyone 20 seconds or however long it takes me to make closing announcements. I'll start very slowly, and I'm buying time right now.
Before you close, Jared, I know if anyone was, you and I were talking about sometime the way we initially conceived of this as doing it as the Brooklyn Bridge. Then
I was wondering what happened to the Brooklyn Bridge. I didn't want to say anything.
No, it's good. I have it. I struggle. I've got the whole presentation, and I think it's a really cool story. It's like, it's such a great metaphor, like on so many levels. Like it's bridging geographies. Like what we do is, at least what I do as a data scientist, you bridge the statistics and the business, the technology and the data. It was designed by an immigrant. It was built by his immigrant son, and there's so many good stories. It was the first use of steel in building, and it showed the city how to build. I can go on for a long time. It's a great story. I struggled with the transition from what Tesla's doing here to what the Brooklyn Bridge is doing, innovation. So it's a story for another day if you're game for it.
Sounds like we're going to have to schedule you for another talk. I mean, that's just what it's going to come down to now.
Perfect.
Yeah. Well, you're telling us about the Brooklyn Bridge, and I do want to see this talk. I think that will be awesome. We are, even though we now are like a global meetup, we're still a New York meetup, and we would like to see what the bridge had actually made New York City into one city. Before that, the 5 boroughs were separate cities. Well, not all 5 of them. There's probably 2 or 3 separate cities, but they combined.
Manhattan was different before the bridge and after they merged together.
Yep.
Big impact.
Yep. So I would love to see that talk. And while you were talking about that, there's a question: if the chips Tesla is customizing, are they ARM-based or some other architecture?
Custom. They're a vertically integrated company. They pride themselves on the full vertical stack. So much so, what I've heard from people that have worked there, way back when they used to build their own ERP software, but it's their own custom chip. It is designed for massive I/O because of all the dot products that are going on. So it is a chip from scratch that was designed to do deep learning fast.
So it's more of like an ASIC even than a CPU or a GPU.
Yeah, it's very, very, very fast. And then they put a bunch of them together on a board, so they have their own version of a GPU. It's if you put a bunch of smart people together and said, make the best hardware you can for AI and deep learning, is what they aspire to be.
Now I'm curious, who's manufacturing? Is it TSMC, or do they even have their own chip fab, like, or they use global foundries, or?
That's a good question. That's a really good question. You know, they're big on manufacturing. I wonder. It's a
Because chip manufacturing is a
they build their own,
one-player business almost. Not a one-player, but it's a very small field.
or at least maybe out of the gate they outsource it and then eventually bring it in-house.
Yeah, that'd be very interesting.
Good question.
And so the other day, I saw a little roadster. It turned out to be a Tesla roadster. And I never heard of this. I'm sure that's what they originally were making, little roadsters, before Elon Musk got there, I think.
Interesting.
Look it up. It was a pretty nifty looking car. I was so very shocked by it. And nothing to do with all your presentation, but I saw that and I'm like, that's a Tesla? I had never heard of it. And then I looked up before Elon got there. I think they were making these little like a 2-person roadster. It's very cool.
Very cool. I heard a fun edge case. As some of my colleagues were helping me with the articulations, apparently the full self-driving does not work in Toronto. It's turned off.
A legal thing?
The old trolley system is on the wrong side of the road. So people exit out of sides that are not expected. So they turned it off. Tesla turned off the full self-driving in downtown Toronto.
I imagine they have to do similar things for driving in London or in Hong Kong or Singapore, anywhere they drive on the left.
There's a great part of the video I was tempted to put in where they showed this crazy, chaotic traffic circle in India. And there's just a different rules of the road for walking, and it's show no fear, and people and motorcycles and scooters coming out of every direction.
And the honking is important there. Honking is very important. Take that.
Yes, and that's a big part of the thinking behind some of the planning that we saw. So that Monte Carlo, and what I suspect is reinforcement learning, is in part intended to overlay the value system onto those traffic systems and make it a more generalized solution across different traffic contexts.
That is really awesome. I think we have exhausted all the possible questions. So I want to give a big thank you to Bill. I'll give my golf clap here. Hope everyone can give a virtual golf clap in the chat. I had a fantastic time learning. It's always fun when Bill gives a talk.
Yeah, I can't wait to see you in person again.
Hopefully soon. If someone gives us office space, maybe BMO has office space, or anybody else can give us some space, we'll do it again in person. So that everyone, check your company has like a cafeteria area with a projector they want to host us in. Check your company. Come to the conference June 8th through 10th and use discount code NYHackR to get a 20% discount. Check out the Manning books. Get your discounted books, get them on a discount. The next few meetups, we have some speakers lined up. We're trying to see if they're going to be in person, so we're not announcing anything yet. But April, May, June, we'll have speakers every month. And just want to make sure let me make sure I'm not forgetting anything. Give me 1 second here. Oh, if you're looking to hire, go to the job postings channel of the Meetup and visit our new website, nyhackr.org. Same address, brand new website, far better than it used to be. So everyone enjoy that. And remember, there's 12 years worth of slideshows, 13 years worth of slideshows, and videos, probably 7 years worth of videos. There's so much. And also the rstaff.ai, 7 years of videos up there too. So lots and lots of content to learn, lots of good stuff out there. Everyone have a great night. And thank you very much again to Bill. This is really excellent. And we're going to have you again back for the Brooklyn Bridge. Thank you, Bill.
Awesome. Thanks. Be good, everyone. Have a good night.
Bye.